Good afternoon. As you heard, I'm the replacement of Ronald Hansen, which is a nice chance to talk about hardware. As you can see, it's pretty much similar to what Ronald anyways would do. We work with photons, and I would like to show you and use the next 20 minutes to give you some insights why photons in our eyes and our opinions are a nice system. I'd like to show you also some nice twists that basically you might not have heard yet about quantum computers, and we in Vienna see the interesting applications. So the research is done in Vienna. We are embedded in this Vienna Center for Quantum Science and Technology. We are currently 13 groups covering very different research directions. Oops, it's the wrong button. Very different research directions, which is nice because still at these days we need expertise from different fields that basically can be used for improving quantum computers to get out of the common thinking and basically speeding up to get to scale up things. So to please Jason, I'd like to show this cover page of The Economist. It pretty much shows the current situation. It's a head-to-head race, still a head-to-head race among quantum computers and the system you prefer. There's ions, there's photons, there's superconductors. And this head-to-head race is great because it means we have to learn from the others. Some are sometimes more advanced than their own system, for example. But it's still new physics, okay? And we learn about how to control individual quantum particles. So it's the best thing, I think, for the community to have this race and these different systems currently basically in the race. Working with photons, I think there's a nice system because they're very rich in the application. So they're the obvious choice for communication. You can even think of optical repeaters if you want. So you can also use photons there. They have been there for the foundations, of course. And the thing I like to focus is there a pointer actually of this device? Don't think so. Okay. Mechanical pointer, okay. And you can use them for computing as well, okay? And the nice thing is, by just using one system, one physical system, you can combine different tasks, which I would like to show in the next few slides. Benefits, the benefits are they're very robust. Basically, they don't talk to each other, which is good and bad. It's also challenging to make gates, but there's a way for doing that. They're very fast, they travel at the speed of light, obviously. And I think that's a super great advantage is they don't need vacuum chambers, they don't need cryostat cooling. In principle, you can run them at room temperatures, which makes them probably in the large scale picture very, very nice and very feasible. The last point here, actually, if we would have had more time, because literally this morning I was informed there's a talk, and then I had to basically on the cab ride and while being in the plane, making the slides. If it would have been more time, I would like to elaborate more on the last point, because these days, where venture capitalists jump in, where engineering companies get aware of quantum computers, we get a great chance to use engineering know-how that's out there for optics. Silicon photonics, telecommunication industry, they basically have all the technology that would allow or at least boost dramatically the scalability or basically scale up the building of a huge photonic quantum computer. So what we aim to do right now in Vienna is we like to focus on particular tasks that we think are interesting. The left one here is our signature, that's security, secure quantum computing. Of course, we also follow general schemes of computers. And in the last line, you see our efforts to make things small scale by integrating the sources, using diamonds, for example, so NV centers in diamond, as well as basically using photonics, integrated photonics for processors. Let me show you some twists where we use photons for showing these kind of applications. In my eyes, the biggest advantage in the future will not be the speed up for doing material science, which of course is very important, but for me, that's basically a personal opinion, the more important or even broader application is security, okay? Because quantum computers allow a hitherto unknown level of security. In a sense, you can really hide your data in the computer. The question, the challenge for that, can we process encrypted data, or is there a chance for cloud computers and so on to have basically the client's data protected, yeah? Not known, not accessible to the computer, goes back to the late 70s when one of the fathers of the quantum, of the regular encryption codes, Rivest, yes, thought, can we go beyond basically encrypting the communication? Can we also encrypt the data there at the computer? And it was thought, no, it cannot be done. Actually, it took 30 years to find a solution, and currently the best solution is using quantum computers. To make it short, Quantum computers allow to build quantum clouds, or basically client-server networks, where the client with very simple, very feasible resources, doesn't need to be a quantum computer. It can be like as simple as just qubits. You can really delegate your computation, your task, that the computer gives you all the performance, all the speed up, all the things you like to do, but in a secure fashion. He doesn't know the input, nor the software, nor the output. That is different to nowadays cloud computing. Please be aware that everything that you do with the cloud, Facebook, Gmail, your internet account, just the communication to the server is secure, but there it must be still plain text for processing. And obviously facing nowadays this cloud world, this cloud computing world, it's of course interesting to protect your own data, that nobody else has access to that. And here we think that in the big picture, when we think about the next 20 years or so, that probably might be the biggest application, in our opinion, for quantum computers. And the first work was called blind quantum computing, because the computer stays blind during its computation. Without going into details, the concepts are rather simple. It's basically a fusion of well-known concepts from quantum cryptography and the benefits the quantum computers have. And this altogether gives you this blind quantum computing. This really allows to have a framework of this cloud network where a client delegates his or her computation. So as I said, here we think that in the future there might be only a few computers available, or you can basically, or you see a huge market by building just one or a few, which you make accessible, as nowadays IBM does, to the entire community. And here, of course, protecting the client's data is a key issue. We might think in the future you might have those optical networks talking to computers where you can secure your own data and still get all the benefits from the computer. Talking about research, as I said, it's more like a hardware talk and academic side. We still like to investigate new twists. On the way of building quantum computers, we learned that there's a huge area of so-called hybrid solution. That means we can combine classical computing, nowadays perfectly available, with feasible quantum technology. And for example, out of these security issues, we realized it's not that hard to make classical computers secure, in the sense you don't get the speed up as quantum computers would provide you, but you can still hide software or client information in a previously inaccessible way. Okay. Second twist about photonic quantum computers. During the technology improvements to get things smaller, basically talk to industry, to get access to photonics and so on, there was a generation jump. So back in the days, setups looked like this for doing simple computations. As you can imagine, that's not the best way to think of how to process thousands of qubits because of these bulky arrangements. This opened the door to methods based on integrated photonics, where you can really minimize your computers and your circuits. And nowadays, you see they look like this. They're like a few millimeters long, can operate at room temperatures, and can really control with a very high precision, 20, 30, 40, 50 modes as you wish for photons. Having access to this kind of stable processors for photons opened a very nice direction for computations that use this interference when being processed. Or they're basically built on using so-called random walks. Okay? As shown here, random walks is just basically paths that are combined and allow photons to interfere. Using these integrated circuits, you can make them small and stable. That's needed for photons. But the nice thing out of this kind of direction was the first ideas for this resource-efficient computations that allow to demonstrate quantum supremacy actually were based on those concepts. And it was, a few architectures came up, and bottom line is it was shown that we have rather feasible number of qubits, in the order of 40 to 50, as we heard today from Alan with the Google system. There's a chance to really prove or demonstrate supremacy. In other words, there's a way to demonstrate or to get results which state-of-the-art classical computers cannot achieve. For me, why is this interesting? It's really like the same spirit as this car. Does somebody know what this car is? For us, precisely. It was the first car that broke the sound barrier on ground. Okay? It couldn't do anything else. Couldn't turn left, couldn't turn right. Stupid device. But basically, proving quantum supremacy has the same spirit. It doesn't need to be universal to do everything, but it's important still to make a computation that says, yes, we build something in the same spirit. We build a device, a quantum computer, that breaks the classical barrier of computing. And that's the spirit of quantum supremacy. Of course, there's challenges and questions. What does it really mean? Which parameters you choose and so on. But I like the spirit to show, yes, we can. Okay, in principle, once this is done, you're in business. The last twist, you made so much pressure, I'm almost ahead of time. I thought I have, okay, good, okay. The last twist I would like to show is that the mobility of photons, which is intrinsically there, allows for new concepts of computing, which are pretty new. And it allows even to speed up regular or standard quantum architectures that are basically well known or you find in textbooks for quantum computing. No worries, there's just one slide about physics in there, but I'm a physicist, so I like to show those things. So the normal speed up comes very simple from the superposition of 0 and 1. You can basically process at the same time zeros and ones, which give this massive parallelism, all the inputs at the same time, and then you have to find an algorithm that extracts nicely the result you're looking for. However, superposition in quantum mechanics can be also done in time or in terms of gate orders. So a new twist basically is that you think of schemes where you can superimpose different gate arrangements, which when you have a regular quantum computer architecture in mind where once you have 0 and 1s coexisting in superposition, as we heard today from Bob's talk, you have fixed your gate arrangements. However, if you allow also quantum mechanics to superimpose those gate arrangements, then by one shot only you run through different circuits, okay? And that's something which is very nice and shows even nowadays there's still development, you know, there's still so much to do, so much to learn. I think we just started there, what can be done with quantum computers. Choose your favorite architecture, no matter what, but still you will see in a few years from now, amazingly new directions will come up in all possible senses. And that's basically how it works. So in standard cases, you have either first operation and the other one, like the gates, or vice versa. Quantum mechanics allows also to superimpose these kind of orders. And here photons, by being mobile, allow pretty nicely to build devices where you can superimpose those gates, and then you see the speed up. So that's the summary. The speed up basically is you have sort of, we call it like quadratic speed up with respect to standard architectures of computers. So what's the challenge for us right now to build up those photonic quantum computers? The challenge is right now engineering. And here photonics has the opportunity now, thanks to venture capitalists, to startup companies, to making industry aware of quantum computers. We can now basically find a common language to engineers with well-established technologies like silicon photonics, telecom industry, to tell them, look, that's what's needed, okay? We know precisely which path to go. For example, here you see we have to, sources are challenging, but we know in principle how to improve the performance to really build large-scale photonic quantum computers. And photonics industry has this kind of capabilities. We know also to integrate circuits to be compact and stable. This can be done by photonics. And things which are slightly more challenging, but still there are directions how to solve them, is detectors. And the last thing to show is like still taking from other systems, as I've shown before, the rays that we have, from other systems, some benefits, which of course help in some senses to be more compact and more stable. In our case, you think of artificial atoms as sources, or NV centers, as Ronald Hansen would do, for getting also there like benefits or improvements in our systems. Good. That's the last slide. I was really fast, as you can see. So I hope I could show you some nice twists and applications that we think are particularly interesting in general, and where photons might have some advantages to when thinking of implementing them. Security, as to shown the first one here, is, in my eyes, really the main application in the future where quantum computers can improve nowadays situations. And the last thing here is I would like to show is for making the step to really like feasible large-scale computers, we have to talk to engineers, and right now this kind of spirit here where industry meets academia, or academia basically starts into startup companies, or involves into startup companies. We have now this real promising future where things might be built out of photons for photons. Thank you very much.